Hi and welcome. I'm trying to learn particle physics. Today, that means that the rule of three, with three generations of particles, whatever, this is part 2 of it, or part 3. And yes, we're going to read you on, and afterwards we're going to do short impingement training, and if you participate in the short impingement training, that is better at your own risk. Yes, that's all. As the contours of a standard model have become more delineated, it is as if that mysterious photocopying has been carried out right across it. All the fundamental particles of matter, the fermions, seem to come in 3 successively heavy generations. It is an absolute puzzle, says Martin Bauer, a theoretical physicist at Heidelberg University in Germany. Everything would be consistent with just one generation. Why exactly the others are there is just not clear. One way to explore further is to test a principle called lepton universality, which roughly states that all leptons behave alike. It means, for instance, that when larger particles decay, any leptons in the fallout should be produced in equal proportions when their mass is accounted for. So what it means is if a lepton, or fermion, or whatever, if something decays, it should give not 1 lepton or 2 or 5 or whatever, just always 3. In 2014, scientists at the Large Hadron Collider BOT LHCb experiment were studying the decays of B mesons. These particles are made of 2 quarks and can decay in many different ways, making them a pet test bed for physicists. This time, something odd came to light. There were 25% fewer muons than electrons produced, flagrantly violating the principle of lepton universality. Now, where are the electrons? The muons and the tau. Inside of every fermion, and fermions are everything. Electron, muon, tau. And then also the electron neutrino, the muon neutrino, and the tau neutrino. So they're electrons, muons, and taus. The following May in 2014, LHCb, Large Hadron Collider BOT, picked up another odd signal. This time, researchers were looking at a different particle decay that generated either a muon or a tau. Again, the tau particles were produced more often than the muons. Okay, they let another particle decay, and it generated either a muon or a tau. But the tau particles were oftener produced than the muons. The muon not oftentimes enough. Now with decay, maybe you're wondering what it is. I don't really know it. I know that atoms can decay, whatever, like uranium and stuff, but I don't really know it. In 2017, LHCb researchers announced the third strike, a separate measurement of B meson decays, which again, I want to say it clearly, we had all the time bosons. With B now we have mesons, for some reason. It is a B meson. A separate measurement of B meson decay, which again showed about a 25% departure from standard model predictions. The significance of this measurement is not extremely large, but it has become very interesting because it goes in the same direction as other similar measurements, says Albert Pugh at the University of Zurich, Switzerland, who works at LHCb. I don't know if Zurich is pronounced in English. To avoid getting overexcited at such quirks, particle physicists use a statistical threshold called 5 sigma to define when a result can be classified as a discovery. That's interesting. Okay, first year. Now, what did they do? They measured B mesons decaying, and again, 25% more tau probably than, or 35% too little muons. Now, they used the 5 sigma define method. A 5 sigma result signifies that the odds are only 1 in 1 to 3.5 million as a result, like that cropping up by chance without any new physics. Let's do it again. A 5 sigma result signifies that the odds are only 1 in 3.5 million of a result like that cropping up by chance without any new physics. Recently, noises from the collaboration have suggested the original anomaly is only getting more pronounced as more information comes in, but perhaps not quite yet reached that crucial 5 sigma threshold. They have to do it 5 times to be sure. What makes it even more interesting is that 2 now defunct experiments, Baba at SLAC and Bell at Keck Laboratory in Japan, looked at similar decays. The SLAC and the TAK laboratory, whatever it means. No, whatever, two laboratories had similar decays. The Heavy Flavor Arranging Research Group, the Heavy Flavor Averaging Research Group at SLAC added both results to the ones from LHCb. Took an average and arrived at a significance of 4 sigma. Now we're having 4 sigmas and we're close to our 5. Why is it now 1 in 3.5 million? Tantalizingly close. Tantalizingly close, but that still doesn't count as a discovery. We need 5. All the same, the potential find would be so revolutionary, it is important we must take the time to be sure of what we are seeing, says Ellis. If lab universality is broken, the most popular explanation is that an unknown particle appears fleeting during the meson decay and interacts with the various pieces of particle shrapnel, pushing their ratios away from what would be predicted. Let's read it again. If lab universality is broken, that means 1 electron, 1 muon and 1 tau. The most popular explanation is that an unknown particle appears, fleeting during the meson decay, and interacts with the various pieces of particle shrapnel, pushing the ratios away from what would be predicted. I'm going to use the simplest explanation I'm possible to. There's Pac-Man and he eats one of the muons. And we're going to end with that. Now, if you were here for particle physics, you can go directly to the next part of particle physics. We will do now the short impingement training. If you participate in the short impingement training, then it's better to go to ZSFAZ and we do forward shorter circuits. Back, front, and down. Get back, up, front. And backwards. And now we're doing the word lifter. Long arms, strong fists, and bring the shoulders down, hands together. Now turn the arms to the inside. Now the arms to the outside, shoulders down, hands together. And the arms to the inside, shoulders still down, hands together. And the last time, arms to the outside, shoulders down, hands together. And relax. Next exercise, arms up to the outside, hands up the fists. A bit in front with the arms, turn the arms in front, and shoulders down, hands together. And now the arms back, shoulders up, and in front. And again the arms in front, shoulders back, hands. Again, the arms back, shoulders up, and a front. And release. And with that was that exercise, and now we're doing the next exercise, and that is a shrug. So lifting the arms up, and shrugging the shoulders up, and release all down. If this exercise causes pain or any other one, then don't do it. Again, the arms up, shrug the shoulders up, and all down. Again, the arms up, shoulders up, and all down. And the last time. And now, the pencil cut. Arms together and bring them down and to the outside. And one last time. And now the sun line. You can also use a tennis ball or whatever. Have the long arm at the outside. Let it fall down and try to catch it again. And on the other side. And now stretching. Take one arm and bring it in front. The shoulder stays back and down. Pull the arm in. Have flat fingers. Try to relax the arm. Go a bit back with the shoulder and turn the palm a bit up to the sky. And the other arm in front. Shoulder is back and down. Pull the arm in. Have flat fingers. Try to relax the arm. Turn the palm a bit up to the sky. Base muss man schon. I thank you very much and until next time.